Hello everybody, welcome back to Semiva. Today's talk is Davide Dameno's talk. He's our speaker. He will tell us about Calabi's conjecture and all the secrets about Ricci-flat manifolds and also the meaning of life. So, okay, Davide, the room is yours.
Okay, thanks Filippo. I will try not to disappoint you, especially on the meaning of life part. So, this should be the core of this, let's say, this session of seminars about the Calabi conjecture. But the thing is that I'm not proving the whole Calabi conjecture in the sense that I will skip many technical details just for a matter of time. But I will try my best to give you the main ideas to show this very important problem. So in Letizia's talk, we saw a bit what a Kähler manifold is, and we learned the basic properties. And in Filippo's talk, we learned how to connect this definition with holonomy groups. Okay. So in particular, he told us that there exists this condition, which is called Ricci-flat. Okay, Ricci-flatness, which means that if I have a manifold with a metric, its Ricci tensor vanishes identically on the whole manifold. So let me start with a very natural question. So my point is, are there examples, explicit examples, of course, of Ricci-flat manifolds which are not flat and by flat, of course, I mean that the whole Riemann curvature tensor vanishes, so the curvature is identically zero. Okay. So that's the question we would like to answer. And even though it's a very natural question, because of course we're just saying, okay, but we're just imposing that a trace of the curvature tensor is zero. Okay. So it's very natural to ask, does this condition imply the total flatness of the manifold? But even though it's very natural, it's very hard to answer this question. So let me just give an overview. The first answer to this wasn't even given in the Riemannian case, but in the Lorentzian case. I will not go into detail because Lorentzian geometry is not our topic, but basically we have a smooth manifold with a metric which is not positive definite. Okay, so G as a bilinear form has this signature. Okay, so it is not that positive definite at all. But this is the first example we have of a Ricci-flat non-flat manifold, and it's due to, I hope I will write this right, to Schwarzschild in 1916. Okay, so he found out that the vacuum solutions of Einstein's equation, Einstein field equation, okay, with, okay, this is a bit technical, but don't worry. This is something called the cosmological constant, and when it's zero, he managed to find some examples of Ricci-flat non-flat metrics. Okay. But the whole point here is to look at Riemannian manifolds. Okay, so manifolds where the metric is indeed positive definite. So, what about the Riemannian case, which is what we talked about? Well, this is far more complicated because, of course, okay, let's find a way to tackle this problem. Okay, first, it's very natural to look at manifolds that are, let me call them, easy to deal with. Okay, so maybe our first approach could be, why don't we look at something of this form? Okay, so homogeneous manifolds. Remember, Filippo told us what a symmetric manifold is, and all symmetric manifolds are homogeneous, and this is the case. So it's a quotient of a Lie group by a closed subgroup of G, okay? So we can compute the holonomy, for example. They are the easiest manifolds we can think about, but there is a problem that by a magical theorem, I have to check how this is spelled. This is from 1975. If we have M homogeneous, then every Ricci-flat metric is flat. So these manifolds do not provide any example of the, let's say, the family of manifolds we are looking for. Okay, so we cannot hope to find a Ricci-flat non-flat metric in the homogeneous case. And as a consequence, not even in the symmetric case, okay? So we have to move from this family to a harder family of manifolds to deal with, but it's something that Filippo told us about. So we want to look at manifolds with special holonomy, okay? And remember, in Filippo's talk, we saw Berger classification of irreducible non-symmetric manifolds in terms of their holonomy. And he mentioned that there are some cases in which the Ricci flatness condition appears. So, okay, we understood that if the holonomy is the special orthogonal group, it's something too messy, okay? It's too wide family of manifolds because every orientable Riemannian manifold has holonomy contained in SO4, okay? So, okay, let's specialize the whole thing. So we deal with a complex manifold, okay, where J is the complex structure, recall please Letitia's talk, and G is our Riemannian metric. So compact, but also Keter manifold. So in particular, the holonomy is contained in the unitary group. Okay. Maybe we have some hope here because the basic thing is that the Ricci tensor is very easy here. When we have a Keter manifold, we can express the Ricci tensor. And we have something called the Ricci form. Letizia talked us about this, which can be written locally as follows. We have the logarithm of the determinant of the metric, okay? Everything's clear from here? Okay. So we have that this is a real 114 and it's closed. So it's in fact in the cohomology group H11, okay? And in particular is in H2, okay? We have a 114, but the most important property we saw about the Ricci form is that its cohomology class is incredibly important and well characterized. Because we saw that the cohomology class of ρ is in fact a multiple of the first Chern class of the manifold, okay? Which in turn gives us this. This is minus 2 pi of the Chern class of the canonical bundle. Okay. So we have some topological data here. Okay. Maybe there is some hope. And another thing, if the first Chern class vanishes, this is true. If, well, this is, let's say, if this Ricci form, of course, is cohomologous to the zero form. But written in this way, I just mean that we can choose the Ricci form to be zero, as we will see in the statement of the Calabi conjecture. Okay. But this is exactly Ricci flatness. Okay. And this, since our manifold is scalar, the holonomy must be contained in the special unitary group. Okay. So our point is this one. Is it true that if we have a Keller manifold with vanishing first Chern class, we can always find a Ricci-flat metric on it? And luckily, we will see that the answer is indeed yes. Okay. So the Calabi conjecture, well, let's say the resolution of the Calabi conjecture tells us exactly this fact. We have a Ricci-flat metric on any Keller manifold with vanishing first Chern class. So it's time to state what the Calabi conjecture is. I guess the years are, if I remember correctly, these, like late 50s, okay. So the conjecture says that if I have a complex manifold, which also happens to be compact, this is our setting, okay, and G is a Keller metric on M with omega, sorry, it's Keller form. So we saw in Letitia's talk that every complex manifold which has this Keller form closed is in fact a Keller manifold. Okay. So we have this thing. We also assume that there exists a rho prime, okay, real closed 1-1-4, such that its class is defined by this. Okay. This is where the magic really comes, because the Calabi conjecture tells us that there exists only one G prime, let's say, Keller metric such that its Keller form is in the same class and rho prime is its Ricci form. Okay. So this is what the Calabi conjecture tells us. Okay. So in every cohomology class that contains a Keller metric, there exists another Keller metric for every real closed 1-1 form that satisfies this. There exists only one Keller metric such that our prescribed Ricci form, our prescribed form is in fact a Ricci form. So what are we saying here? Is that basically solving the Calabi conjecture is essentially solving what in differential and Riemannian geometry we call a prescribed curvature problem. Okay, so basically we give a curvature, or well, something that we would like to be our curvature, and then we try to say, okay, but there exists a metric for which our prescribed curvature is exactly the curvature we want, or is the curvature of the metric. And make no mistake, in general, these problems have no solutions. Okay, so for instance, let's say remark, in general, we cannot prescribe the Ricci tensor on a manifold. The easiest example we can give is that if I want the Ricci tensor to be a multiple of the metric, so we are in the Einstein case, we have severe topological obstructions to that. So it's not always possible. Nevertheless, I encourage you to read this paper by the Turk, I guess it's 1981, which basically says that if I have some sort of invertibility of the Ricci tensor, I can prescribe it locally, okay? But in general, we cannot prescribe the whole Ricci tensor for the manifold, okay? So, why is that important? Why the proof of the Calabi conjecture is so important? Oh, of course, I haven't mentioned this yet, but the Calabi conjecture not only has a solution, but the person who solved the Calabi conjecture was also awarded with a Fields Medal. So Shing-Tung Yau solved. Let me call this CC. So throughout the top, CC would mean Calabi conjecture. Okay. In, I guess, 1976. Okay. Why is this why this is important? Because once we proved the Calabi conjecture, if we impose vanishing first Chern class, we can find examples of Ricci-flat, non-flat manifolds. Not only that, but we can construct manifolds, well, Kerr manifolds, okay, such that the holonomy, which is what we are interested in, of the Levi-Civita connection is contained in this Lie group. Not only that, but if M is irreducible, we have that the holonomy must be exactly this, or this. Of course, this second possibility occurs if M is an even number, okay? And in the literature, now we know that the first example here is what we call Calabi-Yau manifolds, okay? So this is exactly the birth of Calabi-Yau manifolds. The other example is what we call hyperkähler manifolds. I will not talk about them too much because we will have 2 more talks about them. So in our next talk, Zichi will told us something about Calabi-Yau manifolds, and also Benny. We will say something, she will say something about Calabi-Yau manifolds, and then we will kind of dig into the hyperkähler world, okay? But this is important because we saw by Filippo's talk that in these cases, we have a Ricci-flat and possibly non-flat metric. Okay, but we will see an explicit example later. So, okay, we stated the Calabi conjecture. Now it's time to prove it. Well, at least. Yeah?
Sorry, before we move on, maybe I have a related question, not exactly to the Calabi conjecture, but you mentioned about the Einstein manifolds, right?
Yeah.
So I was just wondering if it is completely classified in each dimension, or classification. I mean, is the classification easy or a hard problem in general?
Einstein manifolds.
Yeah.
It's one of the hardest problems in differential geometry.
Oh, okay.
That's
So it's not
best, the authors of best treat you to a dinner in a restaurant stellato. How do you say? Find me an example of Einstein manifolds. Yeah,
exactly. Even find examples of Einstein manifolds is incredibly hard, because many things are known in the four-dimensional case. They are, of course, classified in the two-dimensional case and three-dimensional case, but in dimension greater or equal than 5, it's a real mess. We don't even know if we have, some topological obstruction outside of something like the Myers theorem or something. It's very difficult.
Okay, thanks.
Okay, but I will talk about obstruction of Einstein manifolds later also. And thank you for the question, because make no mistake, but the resolution of Calabi conjecture doesn't tell you anything about Keller-Einstein manifolds in general. We say that there always exists a Keller-Ricci-flat, which is in particular Einstein, with zero scalar curvature if the first-gen class is 0. But if the first-gen class has a sign, or even worse, if it doesn't have any sign, we don't know anything about Einstein metrics. Okay, as we will see later, we can say that the joint work of Oben and Yau, there exists a negative Keller-Einstein metric if this is negative. Okay. But if the Chern class is positive, things are much more complicated. Okay. And we have some obstruction. So even in this case, we can have some problems. Okay. But okay, let's pass to the proof of this conjecture. As I was saying, I will not give, well, I will give you some detail, but the heaviest part is really out of topic here. Okay, so how do we prove something like this? Because it seems incredibly hard, okay? Because we have to deal with cohomology classes, we have to prescribe this strange Ricci form. I mean, it's not obvious at all that this should be true, okay? First step is, let's say, Calabi's genius idea is this. The problem can be heavily simplified. It remains incredibly hard, but it can be simplified, absolutely. So, how do we simplify something like that? We have a very powerful tool, and Letizia told us about this powerful tool, which is the Del-Del-Bar lemma, okay? Because basically, what are we saying here? Okay, we have this strange closed 1-1-4, okay? Yeah, but we also know that this is in here, okay? And if we want to find another 1-1-4 here, then we have this, okay? So by the delta bar lemma, we know that up to addition, we have one smooth function such that we can express this. Okay. And this is the key for the simplification of our conjecture. Because now, okay, we have simplified this. So we take a smooth function, smooth positive function on M, which is defined by this. We get that the Keller form here on omega prime, this 114 is defined as F times omega M. When I say to the power M, I mean the wedge product done M times, okay? Okay, but this tells us that it's a very easy computation, but if I take the logarithm of capital F, this is exactly equal to what we wrote before. Feel free to check it if you want, but it's very easy. So this function, sorry. Well, it's the same, of course, but we have this equation. Okay. These are linear operators, so we can we can do this. This means that this difference is in fact constant. And let me express the constant like this, where A is a positive real number. Okay. Okay, but then we're done. Well, of course, we didn't do anything, but we are ready to simplify the problem.
So can you remind what does DC means, like D bar, the notation?
Sorry?
The D power C, is it the conjugate?
The D bar is the adjoint, yeah. Yeah.
Okay.
Yeah, it's, well, I could use del and del bar, of course, but I'm following, yeah, maybe I'll mention it later. I'm following the Joyce's notation of his book, Compact Manifolds with Special Holonomy, and it's, I think it's a bit clearer if we use D and DC. But yeah, this is exactly the same. Yeah, yeah.
The same as del bar, right?
Well, I mean, yeah, we can express the del bar lemma as we saw in Letitia's talk, even with D and DC, right?
Okay.
So, well, the important thing is that we can think of them as derivatives, of course. And the whole thing is that now that we showed that this holds, now we have this. We have that capital F is equal to AE to the power F. So omega prime M is this. Okay. But M is compact. And since these two 1-1 forms are in the same cohomology class, well, they give us the same volume. Okay. So we have that A integral of this. Well, this is exactly this in terms of volume forms. Okay. But this is exactly the volume of the manifold. Okay. So what are we saying? Basically, we transformed a prescribed Ricci curvature problem into a prescribed volume form problem. Okay. So we are just saying that we have to find a smooth function f and an a bigger than 0 such that this is exactly the volume. Okay, then there exists, and it's unique, a G prime such that the cohomology classes of the forms are the same. And okay, this is a reformulation of the Calabi conjecture. So keep in mind, the Ricci tensor is something that we define by a, let's say, a double derivative, a second derivative of the metric. Okay, so we passed from a problem like that, when we had to find a 0-2 tensor, essentially, to a problem where we can only, let's say, have to find the volume form. So from a prescribed Ricci curvature problem to a prescribed volume form problem. Okay. So we really simplified the whole thing. Okay. Because, of course, now, if the Calabi conjecture is true, if f is greater than 0 and this holds, then this unique G prime such that dVg prime is exactly f dVg. Okay. Everything's clear? Okay. Can we simplify this problem even more? Yes, and so we come to the original formulation due to Calabi, which is the following. So we said that this holds, right, for another, oh, sorry, without the prime, for a function phi. Okay. This holds because omega prime and omega are in the same cohomology class. Okay. Let's suppose that, and we can always do this. The integral mean of phi is 0. Okay. So in this way, we uniquely specify the function here, because this is unique up to addition, okay? So we have the formulation we will use for the Calabi conjecture. Let's say we have a smooth function and a constant greater than 0, such that a integral of e to the power f of dVg is equal to the volume of G. Then what we have that there exists a unique function phi, sorry, which is real, such that this is a positive 114. First. Second, the integral of phi is 0. And third, this is equal to this. Okay. And here we see the true magic of this problem. Because now the problem is just a PDE problem. Because this, well, we can define it locally also if we choose zeta 1, zeta m, holomorphic coordinates on an open subset of M. We have that 3' can be stated as determinant of the metric alpha beta bar plus this has to be equal to a e to the power f. Cross this determinant. Okay. And so we would get that G prime satisfies this relation. Okay. This one, 3, or equivalently 3 prime, is a nonlinear elliptic second order PDE. Okay. We call this a Monge-Ampère equation. And now it's a different story. Now it's a different story because we have all the theory of elliptic PDEs that can help us. Okay. We can solve this PDE. That's the main thing. That now the existence and uniqueness of the metric we're looking for is reduced to the existence and uniqueness of a function, of a real function of M. Okay. So, how do we do this? How much time do I have? What time is it?
It's 3:25.
3:25. And I started at? Okay. So maybe I'll explain this and then we can take, I don't know, 5 minutes of break. So the thing is that, okay, we have a PDE, but it's not the easiest PDE in the world, okay? We really need something to solve this. And this is another genius idea. Well, now it's a standard method in PDE, in the PDE world. But this is a very nice idea. It's what we call the continuity method. Okay. So, what are we talking about? Well, we have this equation, okay? We want to find our function phi. We don't know anything about the solution of this, but we know that a simpler equation always admits a solution. Okay? This one. This is trivial, right? Because phi identically 0 is a solution. So our idea is that, okay, we start from an equation we know everything about. And then we try to deform it to the equation we want. Okay, we try to find a continuous way to transform this equation into one we want. Okay, and I cannot recall what last word I should erase, but oh, that one. How do we do this? Well, the whole point is that, okay, we define t in 0, 1, okay, and a family of real constants such that a0 is 1 and a1 is Ra. So we have a one-parameter family of equations. Omega plus b dc phi t. Okay. These are intermediate equations. Okay. So this is the point. We call S the subset of 0, 1 the set of T's such that, then we call this equation MAT. MAT has a solution. Okay. The whole point here is that if we want to show that the equation we started from has a solution, we want to show that S is open and closed in 0, 1. If we know that, we already know that S is not empty, okay? Because t equals to 0, of course, is in S. So by the fact, of course, that 0, 1 is connected, we know that S has to be equal to 0, 1. Okay. And this is exactly what Calabi and Yau did for solving their conjecture. So a couple of words and then we take 5. This is not so hard. To show that this set is open is not trivial, but it's not that hard because you basically need some argument of, let's say, closedness, in the sense that you need to show that if I have two closed parameters, then I can find that the two corresponding solutions in S are close to one another in some sense, okay? In some, well, when I say in some sense, I just mean in some Banach norm. So we have to find the right norm to define the fact that two solutions are closed, okay? This is much harder. To show that this set is closed is incredibly hard, and this showed the true nature of the genius of Yau, because really here, what do you need to do is that to show that S contains all its limit points. Okay, so you find a sequence of parameters, so Tj, which has a limit, okay, and then you have to show that that limit is in S as well. And in particular, you need to, in some sense, you need to find uniform bounds for the intermediate solutions, okay? Which is done by giving a priori estimates of these solutions. And this is the really hard part. We will discuss it in the second part, but I will be extremely quick because the estimates are incredibly tough, okay? But if we show that the corresponding S in the Calabi conjecture is open and closed, we're done. The only question that remains is, okay, but what about the regularity of phi? Because we need a smooth phi, okay? So at some degree, we will need to define what regularity we're looking for, okay? And apparently, the best thing we can hope for is to define f as a C3 function and phi as a C5 function. More precisely, we will need that phi is in C5 alpha, so it's in a Holder space, okay? But we will discuss it in 5 minutes. So let's take a break, but if you have any questions, I'm here. Okay, we can start again. Zichi made me notice something that I forgot to mention. When I said that in the Keller case, Ricci-flatness is equivalent to having the holonomy in SUM, this is true only if the manifold is simply connected. Okay, in particular, one connected because we need connectedness and simple connectedness. So I forgot to mention this, but we need simply connected manifolds. Okay. So now let me go incredibly quickly, and we try to see the main ideas of the proof. But I will go very fast without details because really we don't have time to deal with that with everything. So, as I was saying, we choose an alpha, okay, and an F in C3 alpha. And we define our S. So the setting is the same I told you about in the part for the continuity method. And we say that Rs is the set of T's such that there exists phi in C5 alpha, okay? Such that is integral over M0 and there also exists an A greater than 0 such that our Monge-Ampere equation has a solution. Okay, so as I was saying before, we need to prove that this set is both open and closed. And sorry again, but I will skip many details here because it's very hard to do it properly. So first thing we want to show, S has to be open, right? So we choose a T prime in S, which means that there exists a phi prime in C5 alpha and an A prime greater than 0, blah, blah, blah. Okay. So there is a result I will not mention, but the thing that is that Yau found that if F prime is in C3 alpha and phi prime in C5 alpha and alpha prime are as before, then if f is in C3 alpha and f minus f prime in norm 3 alpha is sufficiently small, okay, then we can find that there exists phi here and an a greater than 0. I will not write this, but the point is that we can find the phi and a greater than 0 such that the Monge pair equation is satisfied and such that the integral of phi over m is 0. Okay, so everything holds for the corresponding phi and a for this f. Okay, if they are small enough. Okay. Yeah, but in this case, we are basically done. Okay. We are basically done because now, by this result, we can just, instead of f prime, we take t prime f, and instead of f, we take tf. Okay, where t and t prime, of course, where t prime is in S. We need to show that t is in S. Okay, but if the norm of the difference, of which is just this, is sufficiently small, there exists a phi and an a such that we have the integral 0 and the Monge pair holds with t. Okay. Is equal for t. Okay. That's the whole point. Yeah, but what does it mean? It means that t is in S. Okay. So we showed that for every t prime, there exists an open neighborhood of t prime, all contained in S. S is open. Okay. Of course, I skipped many details here, but the main idea is that. So we find that small, if two functions in C3 alpha are close enough, the corresponding phi are close. Okay. Well, no, sorry, it's another thing. If we have an f prime which admits phi prime that satisfies the Monge pair equation, then if we choose another f very close to the initial one, we can find a solution, okay, a corresponding solution. Okay, this was the first part. This is the second part, and this is scary, okay? This is scary because, as I was saying before, we need a priori estimates for phi and its derivatives also. And this is the truly hard part of the conjecture. I will simplify this as the best I can, but if you have questions, please tell me. So, we take a sequence in S that converges to a t prime. And we want to show that t prime is in S, of course. This will guarantee immediately that S is closed. Okay. Since all of these parameters are in S, for every j, there exists a phi j in C5 alpha and aj greater than 0, such that the integral is 0 and this is satisfied. Okay. Okay, this is obvious. This is way less obvious. Okay. Because we define Q1, which is the norm of F in C3 alpha. Okay. Now, the first result by Yau is the following, and I will not prove this because it requires incredibly heavy computations and very careful estimates. Okay. So we know that there exist other three constants. Okay. Which depend on the manifold, of course, on all the structure, but also on Q1. And another constant, which depends on everything I said before, plus these three constants, such that since TJF, the norm in C3 alpha, is of course smaller than Q1. Why? Because the TJs are in S, and so they are in 0, 1. So if its norm is Q1, we are just lowering the norm. Okay. So we have that. These are the estimates I was telling you about. This is bound in C0. The second derivatives, let's call them the second derivatives, in C0 is bound. Even the third derivatives, these are all ij in C0 are bound. Okay, for every j. Just to conclude this, you really have to work hard, okay? But let's take it for granted, okay? By another result by Yau, we know that these phi j, since they are in this, okay, then their norms in C5 alpha is uniformly bound by Q5. Okay, so that's the whole point. That's the whole point, and that's the great idea. We started from a sequence of parameters, okay? But then we found that the corresponding solutions of the Monge-Ampere equations are uniformly bound in norm, okay? And that's the key ingredient, because we know that this immersion is compact. This is the Conocote theorem, okay? This is compact. And this is a bounded sequence, okay? Bounded sequence. We have a compact inclusion. There exists a convergent subsequence. Okay. Phi ij to some phi prime, okay, in C5. Okay. And now I will not write this, but we're basically done, because now we let A prime a constant such that a prime of the integral over e to the t prime f is equal to the volume, the same hypothesis we had before. And so this converges, there exists, the sequence of aij's converge to a prime, okay? But then we just take the limit. We just take the limit and we can find that this is a solution, okay? Because this converges in C5, but so it also converges in C2, okay? So basically, I'm skipping everything, I know, but what this shows is that T prime is in S, okay? And we are done. Because now, S is both open and closed. Okay. Since it's open and closed and 0 is in S, by our definition of S that of course I erased, we know that the Monge-Ampere equation has a solution. Okay. The only issue is that, okay, but we have a solution in C5 alpha. It's not smooth. A priori, it's not smooth, okay? But since the problem is solved, the solution must be smooth, okay? And why is it smooth? Because meanwhile, Yau was proving all the estimates. He's also showed that when you are at this point when you deal with Q5, of course, if you raise the regularity of your F, then the regularity of the solutions raise as well. And so if I have a smooth F, okay, if I have a smooth F in my initial condition, then automatically phi is smooth, okay? So we found that there always exists a solution. Last question, is it unique? Yes. It is also unique. I will not give you the proof, but it was given, I think, by Calabi himself. But it's just a very straightforward argument, okay? You just take the difference of two solutions and you find that that difference is 0. It's just a very easy application of the Stokes theorem, okay? It's not hard at all. You're encouraged to look at Joyce's book to see the proof, but it's very, very straightforward. So, in a very messy way, let's say, and please feel free to ask me anything, because I know this is complicated stuff. The Calabi conjecture is true. And as I told you before, there are many consequences for this. Okay, and the main consequence, I told you that if M JG is scalar, well, sorry, it's compact scalar, and C1 is 0, in each scalar class, which is a cohomology class that contains a scalar metric, or a scalar form, there exists a unique scalar Ricci-flat metric. Okay. Ooh. And as we were saying before, if we also add the hypothesis that our manifold is connected and simply connected, of course, we also will need irreducible to say what I'm about to say. We have the Oloni groups, okay? We have that. If we found a non-symmetric example, we have that the holonomy is this, or the holonomy is this. Of course, here m has to be greater or equal than 4 even. Okay. I will tell you later why I need m greater or equal than 4. But it's simply because SP1 is exactly SU2. Okay. So here we have Calabi Yau manifolds. And hyperkähler manifolds. But as I was telling you before, this is not the topic of today's talk. So I'll leave them to Ricci, Benny, and Lucas. Okay, so we're almost done. I would like to show you some proper example, some geometric example of such manifolds. And since, as you may have noticed, I'm not an expert in this field, I just tell you some very easy stuff about the smallest example of Calabi Yau manifold, which are K3 surfaces. So, what's a K3 surface? In the audience, there are people that knows this way better than me, but I hope I don't disappoint them. So, X is a K3 surface if it is a compact, complex surface, Xj, let's say, with this Betti number, let's call it, equal to 0. So we saw the cohomology groups in Letitia's talk, and trivial canonical bundle. Okay. And the great thing is that all these surfaces have vanishing first-term class. Okay. Actually, one can show that all K3 surfaces are diffeomorphic to one another. Okay. So in particular, this topological properties maintained. Okay. But the thing is that, okay, since this vanishes, and it can be shown that a K3 surface always admits a Kähler metric, then by the Calabi conjecture, the proof of the Calabi conjecture, there exists a Kähler Ricci-flat metric on X. Not only it exists, but it exists for every Kähler class. Okay. Not only that, but K3 surfaces, since the complex dimension is 2, so M is equal to 2 in this case. Well, it's holonomy. Okay. These are simply connected and everything. Okay. So we can use Ricci's result of today to say that this might be contained in this. Okay. But we have no doubt about the holonomy group because these are the same group. Okay. So X is both Calabi Yau and hyperkähler. Okay, very nice. Why is it nice to have Ricci-flat metrics in this? Because very easily, well, not that easily, in fact, but very quickly, we can rule out the possibility of having a flat metric here. How we can do that? Well, those of you which are familiar with cohomology groups, we have a four manifold here. So the cut product is defined in this way. Okay, I chose coefficients in R, but we can choose it. Well, in fact, we will choose them in Z. Okay. But here, by Poincare duality, since everything is compact, we have this. This is a bilinear form, which in turn gives us a quadratic form. And quadratic forms have their signature. So we define tau of M, the signature of the manifold, but in particular of the quadratic form. So recall that we might see this in a matrix way by putting ones and minus ones on the diagonal. And then if we trace this, we obtain exactly this number, which happens to be a topological invariant. Okay. So it doesn't depend at all on the choice of metric. But a very easy, well, this is a theorem, but it is in fact a proposition. But let me state it as a theorem. If I have a Riemannian four manifold with a flat metric, the signature has to vanish. Okay. The converse is absolutely non-true because this is a much stronger condition. Here, to have this, you might just want to have a conformally flat metric, but this is beyond the purpose of this talk. Yeah, but if X is a K3 surface, the signature is minus 16. So there does not exist any flat metric on any K3 surface. But we know that a Ricci-flat metrics always exist. And so we found very easily an example of a Ricci-flat metric which is non-flat. So they do exist. Okay. Actually, I haven't given any example of a K3 surface, but I guess I'll just leave it to Benny's talk. She's way more expert than me in this kind of geometry. Let me say that just one example, the easiest example, which is called the Fermat quartic. Okay, this is the easiest example of a K3 surface, and it's defined in the following way. It's the set of homogeneous, well, points, let's say, in homogeneous coordinates here, in CP3, so in complex projective space, such that this sum is 0. Okay, and there are also other projective examples, like complete intersections of, for example, a cubic and a quadric in CP5, I guess. Okay, and as Benny, sorry, CP4, sorry, CP4. Sorry, it's the 3 quadrics in CP5. Yeah, and also, as Benny reminded me yesterday, there also it can be non-projective or non-algebraic examples can be constructed pretty much easily by looking at some sort of involution that fixes a certain number of points. Okay, And but again, I'll leave the honor to Danny. The last thing I would like, well, the last two things I would like to tell you, and then we can go home, is that apparently the fact that on K3 surfaces there exist Einstein metrics, in particular Ricci-flat metrics, was hinted by Nigel Hitchin. Because there is this beautiful theorem by Hitchin. Sorry, this is 74. Yeah, it's not Z4. Yeah, absolutely. So, what does this theorem tell us? If we take X, a compact Einstein manifold, so the Ricci tensor is proportional to the metric, okay? Oh, sorry, this has to be of dimension 4, real dimension 4, okay? Then, and this should answer to Krishna's question, we have this spectacular inequality where chi is the Euler characteristic of the manifold. Okay, so this is something that we all know. This is the same signature I told you about. This is called the Hitchin-Thorpe inequality. Okay. So this is a severe obstruction to the existence of Einstein metrics on for a manifold. And the problem is that the converse is not true. And again, so let me, as a remark, the converse is false. And it was proven by Liberty. Okay? Because there exist many manifolds for which this is true, but they cannot admit any Einstein metric. Okay? So unfortunately, this is not a characterization. But why did I tell you this after telling you about K3 surfaces? Because Hitchin managed to characterize the equality case as well. So we know that this holds if and only if X is flat or its universal cover is a K3 surface. Okay, and in this case, it's almost easy to see why this guarantees that the scalar curvature is 0, and then we have Ricci-flat. Okay, this is a bit harder, of course, because you have to use some algebraic geometry tools, but it's not impossible to show, of course. But the interesting thing is that Hitchin did not know at all that all K3 surfaces admit Einstein metrics. So the big deal he does in his paper, he says, okay, this is very nice, but we don't know if this thing admits an Einstein metric. We just know that there exists a characterization. So if it's Einstein, it has to be Ricci-flat, and vice versa, of course. And also, we know that if there is an Einstein metric here, we also have a quaternionic Keller structure. This is an if and only if for K3 surfaces. But the thing is that he didn't know about anything about the existence of Einstein metrics. Okay. Last thing, and then we can go home, is a strange relation between the Calabi conjecture and other problems. And this is, well, I just introduced this thing, but I will not give you, not even the details, I will not give you any explanation, more or less. Okay. So, as you all know, the Poincare conjecture has been proven. Okay. And it has been proven by means of geometric flows, in particular Ricci flow. which simply is an evolution equation that tells us that the metric evolves in the direction of the Ricci tensor, okay, with a minus in front of the Ricci tensor. But here we are in the Keller world, so we can define the Keller-Ricci flow. I just give you the definition, and then I'll talk about this very. In this case, so what does it mean? We start from a Keller metric. Here I speak in terms of forms, but it's the same thing, okay? We start from a Keller metric, and then we write an evolution equation, which tells us that these are Keller metrics, and they satisfy this. So this flow preserves the Ricci tensor, of course. Well, it does not preserve the Ricci tensor, sorry. It preserves the fact that this is a Keller manifold, okay? Why is it important? I mean, first and foremost, geometric flows give us information about the topology, because this really modifies the shape of our manifold, okay? The problem with geometric flows is that, okay, we're not sure if this solution exists for infinite time. Actually, in a lot of cases, in the majority of the cases, this stops to be true in a finite time, okay? So we can characterize with the Keller-Ricci flow what is the maximal time existence, okay? And this, by the way, this is not elliptic anymore. This is a parabolic equation. But strangely enough, but not that strangely, to prove that there exists a short time existence of the flow, what do? You take this and you transform it into a Monge-Ampere equation. You do a priori estimates, and then you get that you have existence for a short time, okay? And this short time, let's say, is characterized. So we have a characterization of the maximal time, which is the following. Is the supremum of t, for which this cohomology class, no surprises here, right, is in the Keller cone. What's the Keller cone? Is the set of all cohomology class of 1-1 forms that contain a Keller metric or a Keller form, okay? And this is really the last thing I want to tell you. Why did I mention you this? Because in 1985, we had another theorem by Zhao, which is essentially the Calabi conjecture. Okay, if M is compact Keller with this metric, this is the usual notation in holomorphic coordinates, we take a closed 1-1 form, okay, such that I guess it sounds familiar now, but let's put it this way, locally. Okay. Then, if we take the heat equation, which is very close, as you can imagine, to the one I wrote for the Keller-Ricci flow, this is the Ricci tensor, and these are the coefficients of our form rho. Well, the thing is that by deforming our metric in this way, we obtain another Keller metric whose form is in the same class of the Keller form of this, okay, such that that rho is its Ricci form. So the same thing can be proven by means of geometric flows. Okay, this is just, well, it's tough. It's not much easier. It's not easier than the original Yau's proof. But the whole point is that we deform that our metric by means of the Keller-Ricci flow, and then we obtain the same conclusion of Calabi. Okay, and that was very nice to discover, but I mean it's way beyond our the purposes of this talk. And I guess I can stop here. So thank you.
Okay, thank you, Davide. Are there any questions? Okay, if there are no questions, thank you again. Stay with us for the next talks, as you already know them, that I told about, and hope to see you soon.
Okay.
Bye.